So welcome everybody to the online seminar series on machine learning needs mathematical optimization. So we have the pleasure today to have Víctor Blanco. So he's associate professor at the University of Granada. So this is at the business and at economics and business school. Víctor did his PhD at the Universidad de Sevilla, yeah. And he has done extensive work on facility location, computational algebra, and has moved to machine learning. So together with colleagues from Universidad de Sevilla, he has funding from the foundation BBVA, which has given money to them to analyze complex networks with the use of mathematical optimization and machine learning. We are extremely happy to have here Víctor talking to us a little bit about, halfway data science and location analysis. Thank you so much for accepting our invitation. The floor is yours. If somebody has very urgent questions, you can write them in the chat and we will stop Víctor. Otherwise, as usual, we leave the questions to the end of the presentation. Thank you very much again.
Thank you, Dolores, for the invitation and all the organizers for these great seminars, this great idea on trying to see the synergies between machine learning and math optimization. Well, today I would like to talk about this connection between location analysis and data science, in particular in the designs of machine learning tools using some techniques that have been widely used in location analysis during the years. Well, first, I would like to acknowledge the support of the projects in which I am involved. This Junta Andalucía, Ministerio in Spain, the Foundation BBVA, and for those which are not familiar with location analysis, the main goal of location analysis is to find optimal positions of a service or more services, trying to satisfy the demand of a set of entities. This is a very general definition of location analysis, and the most common application of this field are when we have as entities a set of users, and we have in a discrete framework a set of potential facilities, potential services, and one would like to select one or more of them in order to satisfy this kind of demand of the users. In this case, select one of them as one of the services to trying to satisfy the users, or two services to satisfy the demand. In another framework, the continuous framework, one has a set of users, which are the entities, and one would like to select one or more facilities in the whole space, as in telecommunication networks, trying to satisfy the demand, one facility or more facilities in the whole space. And the tools which are used to solve this problem are quite different from the point of view of the mathematical optimization. Also, one may think on trying to find this optimal, whatever it means, on networks, trying to find the location, find the position of the services in the space induced by a network, one facility or two facilities, or even in more sophisticated frameworks as in hub location, in which the final goal is not only to satisfy the customers in the sense of transportation costs, but also in the sense that each user wants to send some type of flow among a network, and one construct the hub networks in order to transport this good between the users. And it's also one of the well-known facility location problems. Right. There are tons of applications of location problems in many fields, in many areas, from grid location to drones, which are more actual in healthcare, etc. And also the type of models that one can try to, which are already known in facility location, depends on the framework, on the type of entities or type of users, the demand, the nature of the services or the facilities, the nature of the data involved in the problem, etc. So one can see in the second edition, which is the one which is here in this slide of the book of location, recent book of location science. One can see many of those type of problems. Okay. From the point of view of mathematical optimization, one can see, or one can try to write a general model for location problems just by using that one has a set of users, A, a set of feasible services, X, and a measure of how good is a facility or a set of facilities for this set of users or entities. And the final goal is to minimize this function. This function can be can have a very different structure depending on the type of users, services, or final goal of the problem. And the origins of this problem come from the so-called Fermat-Torricelli problem, since Fermat proposed in a letter to Torricelli the problem of finding the way of, given 3 points on a plane, how to construct another one, minimizing the overall sum of the distances to the 3 points. And then Torricelli provided a geometric way to construct this point, which is actually a service in our setting, in our framework of location analysis. The connection between this geometric problem and the management science, or the more modern framework for facility location, was given by Weber at the beginning of the 20th century, trying to, identifying points on a plane with users and other points, which are the services, as other points on a plane or in a more general space. And there are geometric, more well-known algorithms, the base algorithms solving the problem, or more modern tools as second-order optimization, which are useful for solving this problem efficiently. And the generalization of the problem to more than one facility instead of one, which is known as the multi-facility Weber problem, which instead of trying to minimize the overall sum of the distances, when one has more than one service to locate, one needs to measure the distance between each of the points with the closest facility which is located. Okay, and then for this problem, which is more complicated in the sense that we need to determine in the problem which point, which user is allocated to which service, then we need to use tools from mixed integer second-order optimization for norms which are usuals in the sense that they are norms, they are LP norms or polyhedral norms. Okay, so we'll let you move from location analysis to machine learning, and the connection comes from the location of dimensional facilities. If instead of locating or finding optimal position for points, one try to find location of other high dimensional structures, as lines, hyperplanes, circles, etc., then we are in the framework of location of dimensional facilities. There are many works done in this area from different fields, from mathematical optimization, location analysis, but also in computational geometry and statistics. There is a very nice book by Anija Schobel. It was in the 90s, and in the recent book by Location Science, there's a chapter which is very interesting on this general framework of location. So I will turn into the topic of my talk, which is how hyperplane location is interesting when trying to design machine learning tools. Right? And this is the outline of the talk. From location analysis, we will go through the location of hyperplanes, how the location of hyperplanes is going to be interesting when designing tools in supervised learning in two different branches. First, on the design of tools for fitting linear models, regression models, and in the sense of classifying using classification tools based mainly on supervector matchings. Okay, so let's go to the first application, the first connection, which is about fitting points by hyperplanes. In general, when we think on the problem of fitting a curve or function to a training data set, just as the problem of finding a function, such that when evaluating the function on the different observation in my data set, it is approximately zero. When the functions are fixed to be linear, then the problem is to find the hyperplane so that when evaluating it is close to zero, which is closely related to the estimation phase of a multivariate regression problem, which is we fix, which is the dependent variable, imagine the last one, the last feature, and then we try to find the hyperplane, which is approximately this dependent variable, right? For us, there are two main ingredients when trying to determine which is the best fitting hyperplane. One of them is the measure of how far is an observation of being well modeled by a hyperplane. How close is an observation of being represented by a hyperplane. And once each of the which are called the residuals, right? The errors. And once all the residuals are known, imagine we need to have a global measure of how good is the hyperplane that we are constructing, right? This is the aggregation measure. So with these two ingredients, we may think on solving the problem of fitting a hyperplane to a set of data as the problem of minimizing this aggregation function on the set of residuals of the training data set. So in this recent paper with Justo Puerto and Román Salmerón, we designed a mathematical programming framework to this problem, the problem of finding a good hyperplane in a very flexible setting, in the sense that we are going to measure residuals in a very general way. I will show you in a minute, and very general aggregation measures that extend many of the measures that have been already used in the literature when trying to estimate linear models. All of these with mathematical optimization tools. So first, what about the residual? How do we measure residuals, which are the measure of how far is an observation from a hyperplane? We use distance, projections point to hyperplane, right? And trying to generalize what is done in classical linear regression, in which vertical distances are used. In classical regression, in ordinary least squares or classical regression, one select the dependent variables and try to measure how far is vertically in this line, which is on a plane, what is the error with respect to the evaluation of the hyperplane with respect to this variable. But why not to measure this error with respect to other distances, as for instance the orthogonal distance, which is the L2 distance to the hyperplane, L2, L1 or L infinity norm, or other norms, which in many cases may be convenient when trying to have a global model in the sense of closeness of trying to capture the trends of the data set. So using a result by Mangasarian in the 90s, we know for any norm how to compute explicitly the residual when projecting a point into a hyperplane using the dual norm of the norm we are using, right? And using this expression, we can also compute the response when we fix dependent variables, and we can also measure the marginal variation of a feature of a variable when all the other variables are assumed to be fixed, constant. Actually, for well-known norms like the L1, L infinity, or any LP norm with p greater or equal than 1, we know the explicit expressions of these projects, these residuals. Once the residuals are computed, we need to aggregate them, because, well, there is a paper in the 90s by Emilio Carrizosa and others in which they analyze how this problem is, well, the nature of the problem when one has a residual is to try to minimize simultaneously all the residuals at the same time in a multi-objective problem. But in practice, it is difficult, and then it's much better to aggregate to get overall measures of the global error of a model with respect to a training data set. And then the final goal is to find, given an aggregation function, how to compute these coefficients of the hyperplane. Right? So, which type of functions do we use for aggregating the residuals? We use a very general set of family of functions, which are called order weighted averaging functions or order median functions in location analysis, that consist of a sum given some weights lambda, which are multiplied by sorted residuals when the residuals are sorted in non-increasing order. I mean, we have weights which are associated not to residuals but to sorted residuals, in the sense that the first residual, which is the smallest one, is associated to the lambda 1 weight, the second smallest to the second lambda weight, and in this way we are able to model many of the statistical functions that are commonly used, as the sum function. If we fix lambda, all the lambda equal to 1, then no matter the sorting, so have the sum of the power fifth power of the residual. But if we choose lambda as all the elements in the lambda weight 0 except the last one, we only matter the last residual in the list, which is the greatest one. So we are maximizing or trying to model the maximum of the residuals. but we can also model the minimization of the maximum K or the K largest residuals, which is the trim mean or the median, by selecting only the mid lambda equal to 1, the quantile, etc. In this way, many of the classical, well-known approaches trying to for finding optimal hyperplanes fitting a set of data sets can be cast under this general framework as the classical least sum of squares, just by setting lambda all equal to 1, or, well, and the power of 2, or the least absolute deviation, or least quantiles of squares, or Bersimam and Sunder, in which we select one of the quantiles to minimize in the function, or the least trim of squares, etc. In this case, all these cases are designed in origin only for vertical distances. In our case, we also apply this tool for residuals, which are defined as projections from point to hyperplane. So the model, the fitting hyperplane model that we propose, is the problem of finding the coefficient, given a training data set, finding the coefficient of the hyperplane, minimizing an order median function, or with a given set of weights, of the projections from each of the observations to this hyperplane. Then we provide mathematical programming formulation for the problem using an approach that we already applied, or we already somehow discovered for a facility location problem, continuous facility location problem some time ago. And for some cases, we were able to reformulate the problem as a mixed integer second order programming problem, in particular for polyhedral norm, for projections which are based on polyhedral norms in which the balls are polytopes. But for the case in which the norms are not polyhedral, then the relaxation of this problem is not even convex. So we provide an approximation algorithms based on approximating non-linear norms by linear norms, right? And also for large size instances, we apply aggregation techniques for solving the problems more efficiently. Using the same ideas that are used for the R squared in linear regression, classical linear regression, we also extend this measure using a goodness of fitting, using the values of the optimal values of this problem, which is the overall sum of the residuals with this order median function, and also the optimal value when the hyperplane which is being fit is constant. It's the same idea as in the classical regression models, right? And well, we run many examples and many experiments with this general tool, and actually we proved somehow that many choices of lambda powers and residuals are useful when trying to construct fitting hyperplanes, fitting models, linear models, which are robust under outliers observation, right? More recently, actually, this already published in January, February. We extend this problem to the problem of locating not a single hyperplane, but p hyperplane, more hyperplanes, in order to capture different trends on the data set, trying to see whether different observations in the same training data set have a different trend. And then we provide this is the same as extension from the Weber problem to the multi-facility Weber problem. It's from fitting a single hyperplane to the multi-source hyperplane problem, in which not only we have the difficulty of solving a problem for the hyperplane and trying to measure residuals and modeling this order median function, but also the allocation of points to its closest hyperplane with respect to this projection. So this problem is much more difficult to solve than the other one, and then we designed a sophisticated column generation approach for solving the problem that works much better than the natural formulations, which are huge formulations that are difficult to solve by the solvers. And actually, we provide some techniques for aggregating data sets and solving the larger size instances. Okay, it's another picture. Okay. So this is about the fitting hyperplanes and regression models from the point of view of location analysis. If we turn into classification, support vector machines is one of the main optimization-based tools for designing classification rules, and are based on solving this problem, whose goal is to locate or to find a hyperplane separating the classes, with the goal of trying to separate as much as possible the classes, combined with the minimization of the misclassification errors. As this is a general formulation for this problem, which is well known in when the norm that is used is the Euclidean norm, which is a classical formulation for this problem. But also other norms have been explored, as the L1 or the L infinity norm. Some people have tried to understand the mathematical geometry inside the problem when the norm is an LP norm, the norm that we use to measure the margin or the separation between the classes. But very few is known when trying to go into the mathematical optimization insights of the problem. How LP norm, how this problem, how can we extend the kernel trick or other tools which are widely known in support vector machines when using other norms instead of the Euclidean norm. And also how it can be applied to real data set. And that's what we did last year with Justo Puerto and Antonio Rodriguez Chia. We provide second-order compromise primal second-order compromise formulation for the problem when the margin is measured with an LP norm. We formulate the dual problem and try to see how this dual problem can be exploited to use the kernel trick using a more general structure than the classical kernels, but the so-called multidimensional kernels. And we also provide some ways of solving the dual problem more efficiently using transformation based on a shorter basis. And well, the LP supervector machine is nothing but the problem in which the Euclidean norm, when trying to measure the separation between the classes, is changed by the LP norm of the LP norm of the coefficient of the hyperplane, the separating hyperplane. When using the transformation well, let me go back one slide. When measuring the margin induced by a hyperplane separating the classes, one use a result in which given a norm, the separation is 2 divided by the dual norm, which is used to measure the margin. So for an LP norm, we use the dual norm of this norm, which the LQ norm, such that this ratio, this equation is true. So the problem, the primal or natural problem that we need to solve is this problem, which is exactly the same as before, but using the dual norm of an LP norm, which can be also reformulated as a second order cone optimization problem in case Q or P is greater or equal than 1. It's something that we knew also in a paper that we wrote for solving a continuous facility allocation problem. So anyway, let's go to see whether this primal problem can be written using the Lagrangian dual as is this Lagrangian dual, in which, as expected, we need to use absolute value in the expression of the objective function of this dual problem. But if you are familiar with support vector machines, the formulation, the primal and dual formulation are quite similar to those of the Euclidean norm. But in case P is odd, then this absolute value cannot be avoided. So we have some problem to solve here in order to adapt all the tools which are known in support vector machines. In particular, we need to rewrite this dual problem using the different signs that can appear in this absolute value in order to model the problem for the sake of using the kernel tools. And then, but the problem is equivalent to solving as many of these problems as signs are possible when in this absolute value, right? But using this problem, this dual problem, we are able to compute the intercept of the separating hyperplane and also the decision rule on how to classify a point in a data set. So extending naturally what is done for classical support vector matching. Right? In case we want to extend the kernel trick, which means trying to use the same dual formulation, but where the points are transformed using any feature transformation to a higher dimensional space in order to compute nonlinear separator, non-linear classifiers. In their norm, we know that there are some results that allow to easily construct this type of kernels, substituting each is this generalized inner product by a kernel, the so-called generalized inner product or kernel, right? Which are nothing but semi-definite function, right? And using with the same effort that we solve the classical dual problem for a linear separator, we can construct or we can solve the problem for nonlinear separators. So with a little bit of effort, we extend this kernel trick, but we need to determine where it can be applied and how can we adapt everything not easily to this framework by using the so-called suitable subdivision in order to determine which are the signs in this absolute value which are consistent with the construction, and also defining which is for us for an LP norm which is a kernel. And using this structure, we were able to prove that the same ideas that are used in Euclidean supervector machine can be applied for LP norms. And as particular cases, we have the classical supervector machine methods. Right, and the other problem is, well, in supervector machines, it's easy somehow to construct kernel functions that can be applied to the dual problem in order to determine nonlinear separators. In this case, instead of using semi-definite function, we use tensors, earth order tensors, the same ideas apply. Yeah, we have some technical results that allow to extend the so-called Mercer theorem. Right. So in order to solve this problem, the dual problem, which is the key point in supervector machines, then we need not only for the linear separation, but also for the nonlinear separation. This problem is difficult to solve, but we use a different approximation of the problem using SDP relaxations, or even using a shorter basis for approximating the Fisher transformation that are used when solving the dual problem. Well, this is quite technical, but anyway, the main idea is that we extend the well-known tools for solving the supervector machine technique on Euclidean norms, but for more general norms, and many of the ideas under the kernel trick, which are very useful when trying to classify data set, can be also applied. Right. So, and we actually apply this tool, these mathematical programming models to some data set with different number of observations as features, and these are the accuracies. It's only to give you some ideas about the accuracy of this problem with of the LP norm supervector machine for different norms and different data sets. And it is not clear, or our conclusion was that it is not clear that the Euclidean norm is the best norm when trying to classify data set using supervector machines. In some cases, it's quite convenient to use other norms, since it seems to capture more information about the data set. Right. These are the times which are tiny, solving these problems with second order comprogramming, or with the dual formulation. Right, and the last problem I would like to show you today is also on finding optimal hyperplanes, but in this case for designing tools in multi-class classification. There are many tools that use mathematical optimization for designing these decision rules in classification. The most natural or common or popular are the 1 versus 1s, which consist of given the data set with the training data set with the classes, construct the binary supervector machine with one of the classes against the others, construct in this case the 3 hyperplanes, and then find this classification rule by means of these 3, in this case, hyperplanes. Or the 1 versus 1, which is each of the classes against one of the others, and then in this case, three. And there are also, these two are sequential in the sense that the optimization problems which are solved trying to determine the decision rule are based on solving different subproblems which are based on support vector matching. But there are also some compact formulations for the problem, for this problem of finding separating hyperplanes for multi-class classification at the well-known Weston, Waskin, Kramer, Singer, trying to extend somehow the ideas under support vector machines. Right. There are some more which are new. In this paper with Alberto Japón and Justo Puerto, we also explored this idea of finding a compact formulation, a compact mathematical programming approach for determining a classification rule using arrangements of hyperplanes. In the sense that given a training data set and given this optimal arrangement of hyperplanes, the class of a training observation is going to be given by the cell determined by the arrangement of hyperplanes in which it belongs to. Let me give you some ideas of this technique. The formulation is based on constructing constructing a given number of hyperplanes, M hyperplanes. In this case, maximizing the minimum separation between the classes for each of the hyperplanes. So simultaneously minimizing, trying to find the maximum margin between this minimum separation between each of the hyperplanes, which can be modeled using this function, which is the same as maximizing the norms of the coefficient of the hyperplane, and also using two measures of misclassifying errors. One of them is trying to measure points which are well classified with respect to the hyperplane, but that belongs to the margin which is induced by the hyperplane, which with the paradigm of support vector matching is not desirable. And also trying to penalize observations which are not well classified. These are the two errors that we measure in this problem. This is the idea of the errors. We have these this point, which is, it seems to be well classified with respect to this hyperplane, but it's in the margin induced by the hyperplane. And also this circle here is not well classified, so we account for the misclassification error with respect to the cell in which it is well classified. And this is the problem, finding a set of M hyperplanes, minimizing this overall measure of the goodness of a set of arrangements of hyperplanes. So we formulate the problem as a mixed integer or linear programming problems in which binary variables comes from to determine in which part of the hyperplane the observation is, which is the allocation profile in the sense that which class is assigned to which cell, and also to measure this error, the misclassification error with respect to wrongly classified observation. We need to measure how far is an observation of being well classified. And to measure that, when we construct a way of selecting a representative of well-classified observation in a cell, and then we measure the distance with respect to this observation. So we need many binary variables, and once we solve the problem, we need to design the classification rule. In case we have an outsample observation, and in case it belongs to a cell in which in the training data set there is already an observation which is well classified, then we assign this observation to that class. Right, that's the easy way. In case we have an outsample observation and in the cell where it belongs to there are no training data, we don't know which is the class of this observation. So we need to assign a class to that observation. And then we provide a way of assigning this the class as the class of its closest well-classified observation in the training data set. So we need to solve an optimization problem, which in this case is a linear problem, since the integer variables have been relaxed here. Anyway, we need to solve an optimization problem to assign, to construct the decision rule. We also extend the kernel trick to this problem. We can construct nonlinear separators in a multi-class framework using this formulation. And in order to solve larger size instances, we design a math heuristic approach for solving the problem efficiently. Right? We solve different instances from different sources, real-world data sets, this, in which we extend our framework not only for the classical hinge loss misclassification error, but also the RAM loss. So we apply all these formulation, all these models with RAM loss, hinge loss, and not only for Euclidean norms, but also for L1 norms to all the data set. And in many of these data sets, in terms of accuracy, this model outperforms the existing approaches. But in particular, our approach is, well, quite better in case the observations, the training data set, the data set has different cloud points and same class but separated in the data sets. As in this case we have the purple cloud, which is in this corner, and we also have points which are in the same class, which are not in that corner but separated. And the existing approaches are not allowed, because they are not designed for that, are not allowed to capture this difference between the classes. It's not possible to detect these two clouds. In our case, we generate randomly instances with this idea of clouds and classes, with different classes, different sizes, and different settings. And in that case, just using the hinge loss, the one that I told you before, with Euclidean norm, we clearly outperform in terms of accuracy all the existing methods in the literature. So just to conclude, needless to say that math optimization is a powerful tool to model problems in data science, in particular to design rules in machine learning. That many techniques and models that have been already used in location analysis to model problems which are of different nature can be adapted to solve or to construct decision rules in data science. And there are much to do here in the sense that there is much to do on constructing decision rules for classification, for regression, using different schemes to protect under outliers, noises, collinearity, also to detect structural changes, trends of data, and I think it can be done using math optimization, just incorporating different elements to the formulation that we know. So thank you very much. Well, if you have any question, we'll be happy to answer.
Thank you very much, Victor. I think we do it as in previous days, so you can raise your hand if you have a question. I think there was a hand before, but or if you want, you can write it in the chat.
Anyway, you have my email there, so just drop me an email and I will happy.
Yeah, so I think there is a hand. Yeah. But I haven't got it, so sorry. So who raised the hand? Yeah. Or that I think it was the message of Justo, I think.
Justo is friend. Thank you, Justo.
So can you so you were talking about this last example in which you had lots of data. So I guess this one you can basically analyze the scalability of your procedure. I have over
Well,
here because the one after, so where you have
the times you mean?
Yeah.
Or
yeah. So is that something that you have done in the synthetic data set?
Okay. Yeah. No. Well, actually, in the synthetic data set, we generate the instances in the sizes where we were able to solve the problem. But in this case, there is much to do in terms of scalability. It is true that we can always try to combine which is the size of the training data set and try to explore the classification rule in terms of a small training data set. And this is our case. We try to train the model, train the method with a small data set.
Yep.
But well,
yep.
There is much to do here, I think. It's one of the challenges in mathematical optimization, trying to design machine learning tools.
Thank you. And Juan Pablo, would you like to state your question? I can also read it, but I think it's nicer if you...
Yeah, which is a good measure for comparing the traditional statistical methodology versus optimization methodology. Well, I'm not sure in terms of what. If you are aware to design a tool which is interpretable or is protected under outlier observation, then which is the measure? It is not sure. You can use a measure of a robust measure of the outlier that you are detecting or not, but it's not clear which is this equilibrium between trying to solve a more complex model and solving a very easy model. I don't know if it is the direction of your of your question.
Hi, Víctor.
Hi.
I thinking about the first parts. Perhaps we had the traditional O O O L O L O L S, the
Yeah.
ordinary least square.
Yeah, the classical one.
The classical one, yeah. The Markowitz, sorry, the Gauss-Markov theorem tell us that this is the best way to find a regression linear when the data has a normal errors.
Yeah.
Even if the approximation for that is no linear. And that the reason I want to ask in this case how can compare, especially in regression models, no
Yeah, well,
layers, because it's another kind of thing.
Well, in the result that you say, there are some hypotheses that are known to that are needed to say that, which are the kind of distribution of the errors, the so-called the heteroscedasticity, and that homoscedasticity. And we do not assume any of those hypotheses in our models. We construct fitting hyperplanes. We don't know at the moment how to extend this type of fitting hyperplanes to the statistical inference tools that are known for the classical OLS methodology. But for the moment, we have good enough fitting hyperplanes.
Okay.
Thank you very much. We have a question from Maria Joao. Would you like to unmute and ask your question? Yeah, no. I think she's having problems. Okay. Is there any other question? Yeah, Asunción, yeah, would you like to unmute and ask your question?
Yeah, sure. Okay, can you hear me?
Yes, yeah. We can.
Okay.
Hi,
hi, Victor. Thank you very much for the talk. So I really like it. I just have a really fast comment. I didn't note the slide, but I think it was related with the LP-SVM problem with work, and in particular, I'm interested in the results of the column data set that you have from the UCI. Yeah, because this is a data set that I have been using recently in one of my works. And I checked that this data set has outliers. And I don't know if you have noticed also this and you have some methods to solve this problem, or don't know.
Boy, I don't remember that.
Okay.
I don't know. In this case, that we know is that for any
okay, so I remember
we know that the L1 norm was better classifying that, maybe because the L1 norm is robust, is more robust than the other norms.
Yeah,
probably
it makes sense. Yeah,
that's the reason.
Makes sense. Okay, thank you.
Thank you.
You're welcome.
Okay. So yeah, I think we are approaching 5:30. We would like to thank you again for your presentation with lots of new work. Yeah, and you have lots of people. Congratulating your presentation. So I'm not the only one saying that. Yeah. So thank you very much for your contribution to the online seminar series. And we hope to see many in the audience back next week, where we will have a very nice young online seminar series with again 3 young speakers presenting their latest results on mathematical optimization and machine learning. Thank you all, and again, thank you to Víctor.
Thank you.